Hello, I'm Paul Francis, and over the next 25 minutes or so, my colleagues and I will be sharing with you our experiences of using the Schleiermacher method on Project Munin over the past 2 years. The purpose of Munin is to monitor and verify the behavior of another system to ensure that it is behaving as expected. Munin can be considered to be a digital twin of the system that it is monitoring, and indeed that's how it got its name. Munin being one of a pair of ravens that flew all over the world, bringing information to the god Odin. Munin is a multi-domain project, modelled using the Bridgepoint tool and using the Mazel action language, with full code generation to C++ and an architecture supported by Docker containerization. A later presentation today will describe some of the architectural features in more detail. As a system progresses through its various execution threads, it passes through a number of key processing points in its goal to reach a desired outcome. We'll refer to these key points in the processing as events, and the expected sequence in which these events occur effectively defines the behavior protocol for the system. If these events can be observed, then it is possible to verify the behavior of the system by comparing that observable behavior with a specification of what is expected. Using a real-world example, we'll describe the means by which the observable behavior is verified using the Munin Protocol Verifier. Then we will describe how the protocol definitions are defined and provide a short demonstration of how these are used to both A, configure the protocol verifier, and B, to generate event streams that can be used for testing purposes. After the demos, we'll introduce the domain architecture of the protocol verifier and take a look at some example models. We'll then take you through some of the scaling issues that we've been challenged with and the appropriate approaches we are adopting to overcome these. Following the final simulation run demo, I'll then finish off by leaving you with some food for thought by outlining something we call PV prime. We'll illustrate how the protocol verifier, or PV for short, works by considering a system that should be reasonably familiar, an interbank transfer of funds. This is depicted in this diagram taken from the ISO 20020 handbook. Monies are transferred from participant A to participant B following a defined protocol of exchange and supported by a well-defined process which is executed by the system that implements this protocol, the system of concern here. The runtime behavior of the system can be observed by instrumenting it to generate audit events at significant points in its execution. These instrumentation points should be selected to identify key points in the protocol, for example, points that mark the start and end of important sections of processing, or places where parallel threads might be kicked off, fork points in the protocol, or joined back up, merge points. Other interesting points might be where consistency checks could be performed. And there are also points that, if reached, would indicate abnormal, though entirely expected behavior. The audit events generated at these instrumentation points can be compared against the definition of what is expected in order to check, 1, that the correct event types have been emitted, and 2, whether they are in the correct sequence and whether any abnormal behavior has occurred. And if it has, should this be reported as a warning or an alarm situation? For this to be achieved, we need a way of defining the expected behavior in a way that users will readily understand and be capable of specifying themselves. So let's introduce the concept of a job specification. We use a job specification to describe the sequences of audit events that describe the expected behavior of a working system. They can be represented as UML activity diagrams and are specified using a language we call Plus, which is based on Plant UML, a text-based specification. An example is shown on the right here, from which the activity diagram on the left is automatically generated. The example shows a job specification for the financial transaction job that we introduced earlier, with the expected events shown as a sequence which includes forking and merging points, a couple of critical events, which, if reached, represent a point in the protocol which typically indicates achievement of one of the goals of the job, and if abnormal behavior has been detected in its ancestral events, would trigger an alarm. One or more sequenced events, the unhappy events, can also be described, and these describe, if emitted from at runtime, would be an indicator of abnormal, though totally expected behavior. Each job specification can include multiple independent sequences and multiple sections of unsequenced events, if appropriate. One thing that's important to clarify is the difference between a job specification and the instances of audit event sequences. On the left-hand side here, I have labeled each event in the financial job specification with a letter and used this instead of the event names in the example event sequences on the right. Depicted here are 5 example event sequences, each of which complies with the job definition for the financial transaction job. Transactions 1 to 3 are identical and each depict expected behavior for a correctly executing transaction. Transaction 4 exhibits some abnormal behavior, with the unhappy event K occurring in the sequence. However, because there are no critical events, the yellow ones, with unhappy events in their ancestral path, this might only result in a warning. Transaction 5, on the other hand, includes multiple critical events whose ancestors include the unhappy event K. In this case, one or more alarms would be triggered because a critical point in the protocol has been reached, despite an error condition having occurred. And now, a quick high-level overview of how the protocol verifier works. The audit events emitted by the system being monitored are fed into the Munin protocol verifier, which has been configured with a set of job definitions for those systems whose behavior needs to be verified. In simple terms, the protocol verifier then compares the stream of audit events against the respective job definition and generates a set of results that can be used to populate system dashboards, raise warnings and alarms, or even used for detailed debugging of the monitored system. The protocol verifier cannot assume that the order of events that it receives is the order in which they were generated in the monitored system. So the audit events must contain sufficient information to be able to reconstruct the audit sequence. The protocol verifier can be configured with multiple job definitions to support the different types of each system being monitored. And changes to the job specifications are supported without having to restart the protocol verifier. The behavior of the monitored system is reported as a set of results, with each domain responsible for making contributions from the perspective of its own responsibilities. As we'll see later, the protocol verifier can be scaled to support different audit event streaming requirements. I'll pause at this point, allowing us to demonstrate the process of converting the PUML job specifications into a format that can be used to configure the protocol verifier, and then show how the same tool can be used to generate event streams based upon these specifications.
As you saw in the Protocol Verifier system overview, the PV takes input from 2 sources, job definitions and runtime audit event streams. Hello, I'm Cortland Starrett, and I will demo the running Protocol Verifier. Job definitions configure the Protocol Verifier, and runtime audit event streams monitor the operational activity of the system under observation. We look at the job definitions first. The plant UML-based language used to define jobs is called plus. A utility called plus to JSON converts job definitions expressed as plus into JSON, which the PV uses for configuration. Plus to JSON is an application based around an xtUML data model, an Antler4 parser, and Python activities. Plus to JSON is here converting the financial transaction job in its plant UML plus form. Plus to JSON converts the plus into JSON, which configures the protocol verifier. We then produce the JSON into the correct location where the PV will find it upon startup and periodically while running. Plus to JSON needs to understand the job definition well enough to convert it into JSON. So what if it understood the job definition well enough to interpret the job definition? With the plus language parsed and populated into the plus semantics, it became feasible to develop an interpreter of plus. The interpreter navigates plus and plays runtime audit event streams according to the populated job definition. We use --play option to interpret the job definition and play a legal sequence of audit events. I can use -p to see a human readable version of that, and then I can ultimately play to the output terminal or directly into the message broker port and topic, which is how we run in production.
Now let's take a more detailed look at how the protocol verifier is constructed. The audit events emitted from the monitored system are streamed into the reception domain, whose job it is to convert the received events in whatever form they arrive into audit event objects that can be used by the other domains in the protocol verifier. It thus isolates the other domains within the protocol verifier from differences between and changes to the format of these event streams generated by the monitored systems. The audit event objects are then passed to the ordering domain, whose job it is to validate the audit events and then ensure that they are presented to the sequence verification domain in a correctly ordered sequence. The sequence verification domain is responsible for verifying that the sequence of audit events for a given job match that of the respective job specification, taking into account expected use of repeated event types and forks, merges, and parallel paths within those sequences. A job is deemed complete when all sequences within the job have themselves completed. The rules built into the sequence verification domain will detect and report correct behavior and a variety of error conditions. A recent addition to the protocol verifier is the verification gateway domain, which provides support for verifying the behavior of the protocol verifier itself. More on this later. Audit events can include event parameters, also known as event data, which can be of various types. One of these types is an invariant, a data item whose value should be consistent in all events where it is used across all job sequences. Invariants can be used in the monitored system to indicate compliance with system-specific rules. Because it spans multiple job instances, its value must be stored in the protocol verifier for as long as it is valid, so that the protocol verifier can check that jobs are compliant with it. The protocol verifier domains are currently deployed into separate processes to support effective and efficient scaling demands of different monitored system types. More on this from Greg later. Finally, the primary domains within the protocol verifier are supported by domains responsible for inter-domain messaging and logging. Let's take a quick look at one or two of the domains in a bit more detail, starting with the sequence verification domain. This is a data-driven domain. The classes in yellow are specification classes that are used to capture the job specifications in data. This includes the expected ordered sequences and where event data is used. The classes in white represent the runtime audit event sequences for each job submitted for verification. The state model shown here defines the stages that each job progresses through in order to verify its correct behavior. And now a quick look at the ordering domain. Remember that one of its primary purposes is to get the received event audit events into the correct order for subsequent verification by the sequence verification domain. This means holding on to and queuing events that have been received in advance of their ancestors before then passing them on in the correct order. Both the ordering domain and the sequence verification domain can handle multiple jobs in parallel. The state model here depicts the states and transitions that each job goes through until the event stream for that job dries up. With that whistle-stop tour of the Munin domain models completed, I'll pause before we can move on to the next section.
Hello, Colin Carter here with a short video sidebar containing some observations on the modelling within Project Munin. As Paul has described, we're receiving a series of audit events that are expected to occur in a well-defined protocol. So it was natural to consider using a state model to capture the protocol. We did try this, as we reported last year, and a simple protocol was very clearly represented by the state model, but we spotted a number of issues. Where the protocol is a simple sequence, the state model is fine. But if the protocol contains alternative or parallel paths, then the state models rapidly become complex and unwieldy. Next, the system is brittle. Any change to the protocol requires a change to the state model and a rebuild of the application. Finally, to support more than one protocol requires an additional state model for each sequence of each protocol, yet more complexity. So, as an alternative approach, we also tried capturing the protocol in data using specification classes. Defining the data that captures the protocol is therefore key. So we added some tooling to help, and that is where Plus2JSON comes in. We use PlantUML, which provides a standard textual representation of UML constructs and presents them to the user as a really understandable diagram. We tried sequence diagrams first, but found activity diagrams to be a great fit with its support for logic operations and parallel behavior. So we use a subset of PlantUML, which we call Plus. Next, the approach scales to pretty much any complexity of protocol. We have a test protocol we call the kitchen sink job. Any change to a protocol or addition of a new protocol is just a change to the data. So no rebuild is necessary. This eliminates the brittleness associated with the state-centric approach. Next, parallel and alternative paths are easily captured. And we noted that some error conditions could occur at just about any time, which caused the activity diagrams to become complex. However, because they occur at just about any time, there is little or no value in sequencing them. We allow such events to be unsequenced, which dramatically reduces the complexity of the Plus activity diagram. We can support any number of protocols in the system concurrently. It's just data. So the data-centric approach has proved capable and flexible without any significant performance overhead. So that's the approach we have firmly adopted. This shows the class diagram for the sequence verification domain of the Protocol Verifier as it was in March 2022. The yellow classes are the specification classes, which are the ones populated by Plus2JSON, and the white ones are the runtime classes. As you can see, there are just 5 specification classes and 4 runtime classes. One of the claims of the Schleiermacher approach of modeling the world in data is that the information view tends to be more stable over time than a functional view. In March 2022, we only knew a fraction of the requirements. The requirement set has grown since then. But what has happened to the model? Here you can see the current sequence verification domain information model. It has 25 classes instead of the original 9. Also note, as with the original, it is a roughly 50-50 split between specification classes and runtime classes. As requirements have been defined, so we have grown the capability as you would expect. So where did the stability of the information model go? This is the same information model, but with the same 9 classes shown in green, and the original relationships are in green too. That original model is still the core of the model 20 months later. That foundation has proved stable and has supported the additional requirements without having to throw stuff away. That stability has been beneficial throughout the model, including in the action language. Now that's just a couple of observations on the models. I could go on, but not today. End of sidebar. Thanks.
Scaling Munin PV. So if we consider the system that was being monitored from earlier bank transactions, you can imagine there are thousands of transactions happening every minute, and therefore very large amounts of events that need to be verified. So we knew we had to scale Munin PV. So originally Munin PV was one process with reception, ordering, and sequence verification. But if we just span up several instances of that process, what we couldn't guarantee was that the events for a given job would all end up at the same process. So we knew we had to split them apart. So that's where we ended up with a reception process and the PV process containing ordering and sequence verification. Then we knew that reception was only doing schema validation of the event, and therefore reception didn't care which event it received or for a given job. But PV-proc itself, what we wanted to ensure was all the events for a given job were sent to the same instance of PV-proc. That's where we came up with this concept of laning, and I'll talk about that a bit more on the next slide. And then for future scaling, we know there's still a bit of work that we need to do so that we can dynamically scale going forward, and that's where I'll talk about that. So when we broke them apart, we containerized the processes. So reception and PV-proc are managed by a Docker Compose file. Reception, we set the number of instances of reception that we want to run in the Compose file. But for PV-proc, we have to create an individual instance in the Compose file because we need to pass the IDs for the lane that PV-proc instance is managing. So a little bit about laning. So for a given instance of PV-proc, we assign it a lane based on the job ID. So we use the last two numbers in the job ID to determine that lane. So for example, if you look at the slide, there's two instances of PV-proc, and the one instance is processing job IDs that end in 0 to 7F, and the other instance is processing job IDs that end in 80 to FF. This way, when an event is received by a particular PV instance, it can check the job ID for that event against its lane definition, and if it is for that lane, it will process it, and if it's not for that lane, it won't process it. So originally, events were arriving in files, and then reception would read them out of that file, do its work, and then write them back to a file for the lane that was to process them, and then the PV-proc would pick those up from those files. That wasn't performant, so we decided we had to move to a message bus solution. That's where we did some work to introduce Kafka. Introducing Kafka didn't make any difference to the models because it was all in the architecture. So now we have a solution where events are arriving over Kafka at reception, they're getting validated against the schema, and then they're being passed from reception across Kafka to ordering so that they can be processed. And like I said earlier, they are directed to all the instances, and it's just reading that event off the Kafka bus and making a decision about whether it's going to process it based on the lane that's been allocated. This has proved really successful. We're now meeting our requirements, so we're really pleased. But what we do recognize is that moving forward, we can't dynamically scale. So the reason for that is because we're configuring the lanes in the Docker Compose file, we have to bring down the whole system, update the Docker Compose file to add in a new instance of PV and assign it some new lanes and reconfigure the existing lanes. So the future. So we've determined that reception itself doesn't need to be scaled. We've improved what we're doing with the schema validation so that it's performant, and we think we can just run one instance of reception. What we'd like to be able to do is spin up instances of PV-proc as and when needed to meet the scale of the system. To do this, what we're going to do is we're going to introduce a new domain, job management, which will implement just a standard worker pattern. And when a PV instance is started, it will register itself with job management and get assigned a worker ID. Once job management has assigned that worker ID to that PV instance, it will be in the pool of PV instances that it can assign jobs to, and it will just use a round robin mechanism to select an instance for a given job. So that's the future of scaling for Munin PV. Thank you very much.
Now let's put all the pieces together. We know how to configure the protocol verifier with job definitions, and we have run simulated event streams with plus to JSON --play. All that is left is to launch the protocol verifier and play events into it through the message broker. The top terminal is running plus to JSON inside a benchmarking script. The bottom terminal launched the containerized Docker images of the protocol verifier application domains. Performance monitors simply provide eye candy. We are running a single instance of reception, 4 instances of ordering plus sequence verification, and 1 instance each of logging, invariant store, and Kafka. The benchmark runs 10,000 audit events from a variety of job sources. We measure the throughput of 840 events per second.
And finally, back to me again, for the section of the presentation we call eating our own dog food. I hope it becomes clear why. Well, we have already seen how the protocol verifier verifies the behavior of a monitored system. But of course, the protocol verifier itself is just another system of concern, for which we might reasonably want to confirm is behaving correctly. So we could instrument it in exactly the same way as previously described, and then use the event stream that is emitted to verify its own behavior by configuring another protocol verifier instance with a job specification that describes the expected behavior of the protocol verifier. We often refer to this additional instance of the protocol verifier as PV prime. Alternatively, we could configure each instance of the protocol verifier with job definitions for both the monitored system and for the protocol verifier, and then feed the protocol verifier generated events back into itself. The question that remains to be answered is, does this introduce the possibility of any security vulnerabilities? I'll leave you with that thought in mind and move on to a short question and answer session.